Okay, so we're talking about implicit differentiation. The reason we need to be able to do implicit differentiation is because it allows us to find derivatives even if the equation is not solved for y. In that first warm-up problem, this was the equation I gave you. And I went ahead and solved it for y because you don't know how to take derivatives any other way unless they're solved for y. But what this problem was originally was this. So what I had to do to get it into this form was subtract the x squared and then take the square root. And when I take the square root, it's actually plus or minus this, but I just gave you the positive of it because I didn't want you to have to do two problems. So what we're going to talk about today is how can we find the derivative if it's in this form? It's not solved for y equal. And when it's not solved for y, then we have to use this concept called implicit differentiation. When our variables agree, we use the simple power rule. What I mean by the variables agreeing means I'm taking the derivative of x and I have an x term. Variables disagree. We use the chain rule. That's when I'm taking the derivative of y, but with respect to x. When that happens, I have to put dy dx. So here are some guidelines we use. We differentiate each term with respect to x or t. See, a lot of times we want to find the derivative with respect to x because that's going to tell us the slope. Remember how dy dx is the change in y with respect to the change in x? That tells us the slope. But later on, we're going to want to find the derivative with respect to t because that's going to tell us the rate of change with respect to time. The reason that we care about taking derivatives with respect to x is if I have some object that has this kind of a pattern. You can think we have that kind of pattern anytime somebody shoots a basketball, throws a football, shoots off a rocket that's going in this kind of direction. That's a dy dx kind of situation. It can also be in terms of finding the change in the height with respect to time or the change in the x with respect to time. But a lot of times we just want to know what's the rate of change of y with respect to x. But if something is shot straight up and then comes straight back down, a lot of times there's no horizontal component to it. So we just want to know what's the change in y with respect to time rather than with respect to x. So that's the reason why we take the derivative with respect to x sometimes and with respect to time other times. So the method we do is this. We differentiate each term with respect to one of those two. We collect all terms involving dy dt or dy dx on the left. Everything else goes to the right. We factor dy dx or dy dt out of the left side, and we solve for dy dx or dy dt. So let's look at this example. We're finding dy dx for this problem. So what we're going to do then is, I'm not going to solve it for y equals, but we're going to take the derivative. What's the derivative of x squared with respect to x? 2x. And it's really 2x dx dx because the variable I'm using is x and I'm taking the derivative with respect to x. But we don't have to write dx dx because what's dx dx? Anything divided by itself is 1, so I don't have to write it. Okay, so on this one, what's the derivative of negative y squared? Negative 2y. But I took the derivative of y with respect to x, so I have to write dy dx. And now I'm taking the derivative of 25. And what's the derivative of 25? 0. So to solve this then, I have negative 2y dy dx equals, I take the non-dy dx term over to the other side. To solve for dy dx, I divide both sides by negative 2y, and I get that dy dx equals x over y. So the only thing that's new about this is now we don't have to solve this for y equals. That's very similar to the first problem we did in the warm-ups, but I solved it for y equals because you didn't know implicit differentiation. But now you could have found the derivative without solving it for y. So how does this help us? Well, this kind of problem here, if I divide it through by 25, this kind of shape is called a hyperbola. Did you guys work with conic sections, hyperbolas, in pre-calc last year? Okay. So if I have a hyperbola like this, that's telling me that if I want to know the slope right here, I could plug it in. At this point, x is 5, y is 0. 5 over 0 is undefined. Can you see how that's what the slope is? The slope right here, I'd have to know what the point is. Whatever that point is, I'd plug it in and I could find the slope. So that's the whole reason for finding dy dx. Let's try to do it now for this problem. So we have x cubed y squared plus y equals x squared. What kind of term is this? It's a product, isn't it? So if I have a product, I have to use the product rule. I'm going to go ahead and write it out. For this term, f is x cubed. What's f prime? G is y squared. What's g prime? 2y, but then what do you have to put? dy dx. All right, so for this term, I have to use the product rule. So I have to do f prime g plus f g prime. That's just for that term's derivative. Now I go to my next term. What's the derivative of y? Just 1, but then what do I have to put after it? dy dx. So it's plus 1 dy dx. And I would suggest you put the 1. You'll see why here in a minute. I go to my next term. The derivative of x squared is 2x. I want to solve this for dy dx. Here's where people get confused. They're like, how in the world do you do that? Think of a simpler problem. What if the problem had been this? Just 3, let's say 3u plus 2uv plus 1v equals u. It's similar, but a little bit different. If I wanted to solve this for v, can you see how I would get the v terms together and everything else I would take to the other side? So this would be u minus 3u, which would be negative 2u. So that would be gone. And then what would I do here if I wanted to solve for v? Factor out a v, right? And I'd be left with 2u plus 1. So to solve for v, I would divide by this. That's all this is, guys. I want to get this dy dx by itself. So I have to get rid of this term. It has to go over to the other side. I'm also going to rearrange this while I'm at it. So I have 2x cubed y dy dx plus 1 dy dx equals 2x minus 3x squared y squared. Do you see where that came from? These are my two terms with dy dx in it. See how it says collect all terms involving dy dx on the left side, everything else to the right. That's what I did. Now I want to get dy dx by itself, so I have to factor out dy dx. So if I divide this term by dy dx, I'm left with 2x cubed y. If I divide this term by dy dx, what are we left with? 1. And that's why I recommend that you write that 1. Do you see how if we hadn't written the 1, a lot of times people forget that 1? Right? Because you have to think dy dx divided by dy dx, that's 1 right there. And so now we've got this. Are there any questions at this point? Okay, so now I've got this that I'm trying to solve for. It's dy dx times that equals right there. So how do I get rid of this if it's multiplication? Divide. So dy dx then is equal to 2x minus 3x squared y squared over 2x cubed y plus 1. That would be the equation to find the slope of the tangent line to this equation. Notice I'm not saying function. If I did say function, I shouldn't have. This is not a function, is it? Right? And neither is this one. If you were to solve this for y and graph it, you would see it's really not a function. So what we're doing now is we're able to find derivatives of equations that are not necessarily functions. Okay? All right, we're going to switch things up just a little bit. Now we're going to take that derivative with respect to time. And the reason we care about that is because I could have this object right here following this kind of path, a parabolic path. I want to know what's the change in the height with respect to time. What's the change in the distance with respect to time? You can think of how important that would be. If you're going to shoot something off and you want it to land somewhere at a certain time, you have to take all of this into consideration. The change in the x, the change in the y, all of that with respect to time. Okay, down here. I want you to change this to subtraction because it's much more difficult with subtraction. So we're taking this derivative with respect to time. What's the derivative of y with respect to time? 1 what? Not dy dx, dy dt, because now I'm taking it with respect to time. Equals, what's the derivative of 3t squared? 6t. Do I have to put anything after it? No, because my variables agree. I'm taking the derivative of t with respect to t. Now, whenever you have subtraction, I suggest you think of it like this. 3t squared plus negative 2ty. It'll save you a lot of hassle at the end if you think of it this way. The reason why is because we have to use the product rule. And if we have to use the product rule, we would have to subtract the whole quantity if we think of it as subtraction. But if I think of it as plus and negative, I'm not going to have to deal with that. Right here, this is going to be the f. Right here, this is the g. So we're going to do f prime. What's f prime? What's the derivative of negative 2t with respect to t? Negative 2. F prime g plus f, and what's g prime? What's g prime, guys? 1, but then dy dt. When you start doing this on your own and you have trouble, it's probably because you forgot your dy dt or because you forgot to put plus a negative. This will help. All right, so now I'm going to simplify all of this. So I've got 1 dy dt equals 6t minus 2y. I'll just change plus and negative as a minus. Really didn't need to write that again, but nothing to really simplify. So what am I going to do now? If I'm trying to get dy dt by itself, I'm trying to solve for that. I want to take this over here, right? Because I want them on the same side. So I have 1 dy dt, take this over, plus 2t dy dt equals this. What now? Take out a dy dt. When I do that, 1 dy dt divided by dy dt, that's 1. Dy dt with 2t, if I divide that out, that's 2t. And so my final answer for dy dt, which is the change in the y with respect to time, is 6t minus, this was a y, wasn't it? Darn it. Over 1 plus 2t. Okay? Any questions there? All right, let's try one with trig now. taking the derivative with respect to t. Now on your homework, all you're going to do is with respect to x, so it'll seem easier. But I want you to get used to the t's because later on everything's going to be with respect to t at one point. Okay, so 2 sine t. What's the derivative of 2 sine t? 2 what? Cosine t. Do I need to put the t dt? No, it's just 1. Okay, now on this one, when I take the derivative of 2 cosine 2y, first of all, what's the derivative of cosine? Negative sine. So this is going to be negative 2 sine of 2y. But I'm not finished because I have to use the chain rule on this. I have to do times the derivative of 2y. What's the derivative of 2y? 2 dy dt equals, and what's the derivative of t squared? 2t. Okay, that's not so bad. Every term that has dy dt is going to stay, but everything else is going to go over. And I'm going to simplify this while I'm at it. So this right here, 2 times 2 is negative 4 sine 2y dy dt equals 2t minus 2 cosine t. To get dy dt by itself, I have to divide my coefficient of negative 4 sine of 2y. So now this is gone and this is gone. All I did was I multiplied this 2 times this 2. This 2 does not change the angle. It changes the coefficient. We never change an angle unless we use a double angle formula. So dy dt then, if I have this term, and this term, what can every one of those terms be divided by? 2. If I divide this term by 2, do I divide the angle by 2? No. So I divide that by 2, divide that by 2, divide that by 2. And that would be the answer for dy dt. Any questions? All right, I want to show you one more thing, and that's just simplifying a problem. On the problems you're going to do here in a minute, you're going to end up getting something similar to this. Negative 1/2 x to the negative 1/2 divided by negative 1/2 y to the negative 1/2. It's something similar to that, and no one seems to know how to simplify something like that. Would you guys know how to do it? How just to simplify something like that? How would you do it? I could cancel out these negative 1/2, right? These are just multipliers. They're factors. So negative 1/2 divided by negative 1/2 just cancels out to 1. What would you do now? How do I make a negative exponent a positive exponent? Switch it, right? So my x to the negative 1/2 comes down to the bottom. My y to the negative 1/2 comes up to the top. Can you see why this would be our answer then for that? Okay? So when you get things like this, don't just stop and say, I don't know what to do with that. Think about it. You're just dividing these two, and then to change a negative exponent into a positive, you switch the position, and this is equivalent to that. They mean the same thing. All right. Any questions? It's not difficult. It is something you've got to